So today we're going to continue exploring graphing exponential equations. And we're going to use Desmos to kind of get it started to look for any patterns that we see in relationships that will help us when we are graphing them by hand. So here we're going to say our parent function is y equals 3 to the power of x, and that's what's on our paper already. And if you could type that into Desmos, you'll get the same result, and we can see some very distinct points on this parent function. We have one at 0, 1, we have another at 1, 3, and we have another one at negative 1, 1/3. So the first one we want to graph after this is y equals 3 to the power of x plus 3. So if we type that into our y2 on Desmos, we'll get a result looking like this in blue. So if we compare this graph to how our original parent function was 3 to the power of x, what happened? How did it change? And we can see that we had a change of the graph by shifting it up. And you're saying, well, how many did it shift up? Well, let's compare the y-intercepts. Our original y-intercept for the parent function was at 0, 1. Now it's at 0, 4. That moved up 3 units. Also, notice how your horizontal asymptote also shifted up 3 units from where it was before. Our original horizontal asymptote was at y equals 0. Now it's at y equals 3. So all of the outputs increased by 3 units, impacting your asymptote, and it would also impact your range. Now let's take a look at y equals 3 to the x minus 5. So again, here's our parent function, 3 to the power of x. Now 3 to the x minus 5 looks like so. How did it change? Well, this graph shifted down, and again, compare those y-intercepts. We can see it shifted down 5 units, as well as the horizontal asymptote. So again, the domain was not impacted. The range was. If we're talking about the range for this function, we'd have to say that y would have to be greater than negative 5. And again, we've got the interval notation to talk about that. We also have our horizontal asymptote. Very similarly, we could talk about our first other function we compared it to, 3 to the power of x plus 3. Again, it was shifting it up 3 units, no change to the domain. The range is now that y is greater than 3, and that again, horizontal asymptote, y equals 3. So in this equations, we're looking at adding and subtracting a value that we're calling k. And so how does that affect our graph? Well, when k was positive, it shifted up k units, and if it was negative, it shifted down k units. So again, that's going to impact your range and the horizontal asymptote. So if we look at a new parent function, we're going to say y equals 1/2 to the power of x is our new parent function. So let's give you a moment to put that on Desmos. And again, we can see some key points on the grid there that we could use as a comparison as we look at 2 other functions. So if we graph our next function, y equals 1/2 to the power of x plus 2, what results? And it looks like so. If we graph y equals 1/2 to the power of x minus 6, that looks like the function in green. Now, how does this compare to our previous example? Well, our previous ones were exponential growth because our b value was more than 1. Here, our b value is less than 1 but greater than 0, so this is exponential decay. Now, if you noticed, is there a difference that happens between exponential growth functions or decay functions if you are adding or subtracting k to your equation? And the answer is there is no difference. The same rules still apply. If k is positive, it's going to be shifting it up, impacting your range and your asymptote. And if it was negative, it's shifting it down, again, impacting your range and your asymptote. Now, without looking at any graphs, again, let's think about a parent function of y equals 1/3 to the power of x. By looking at that function, we should automatically know that this represents exponential decay. So we have an idea of what that looks like in our head. Now, if we want to think about our new graph, y equals 1/3 to the power of x plus 1, how is that going to compare to the original parent function? Well, it's still going to be a decay because that b value did not change. But if we're adding 1, that's going to impact the outputs. So it's going to be shifting everything up 1 unit from where it was before. So that's going to increase the outputs by 1. It's going to not impact the domain because those are your x's, the inputs. Our range is now going to be greater than 1, so we have our interval notation showing that. And our asymptote, which is normally at y equals 0, moves up to y equals 1 as well. So just by looking at the equations, we don't even have to have a graph, and we can already talk about the domain, range, and asymptotes. Let's try a new parent function. So let's look at a parent function of 2 to the power of x. So let's give you a moment. You could type that in on Desmos. And we can see we have several key points here that we could use as a reference with the coordinates. And we're going to graph 2 other functions with this. Let's first graph y equals 3 times 2 to the power of x and see what results. And so I'll have that highlighted here in green. What changed? Well, it's still an exponential growth function, but notice its rate of change is steeper than it was before. There's a greater difference between those grid points. And so remember, your y-intercept was originally at 0, 1, now it's at 0, 3. Your next point of reference was at 1, 2, now it's at 1, 6. Well, how do you go from 1 to 3 and 2 to 6? That's a multiplier of 3, so it's 3 times faster than it was before for the outputs. We have a stretching going on here. So our domain was not impacted at all. Our range is not impacted at all either, or the asymptote. It's just going 3 times faster than it was before. Well, let's take a look at that other equation. Y equals 1/2 times 2 to the power of x. What does that look like? That's here in blue. So again, a little bit of changing. Notice that there's not as steep of a difference between those reference points. It actually looks like it decreased and it slowed down. It's actually half as fast as it was before if you were comparing those outputs. So it's a shrinking effect, not necessarily stretch, going faster like our previous one, but it's going slower, so we're going to say it's shrinking. The domain was not impacted. The range isn't impacted, neither was the asymptote, but we know that it's half as fast as it was before by comparing those outputs. So when we're talking about this a value, this multiplier of a, how is that impacting your graph? Well, we know if a is greater than 1, it's going to be increasing faster than it was before. A times faster, in fact, so we refer to that as a vertical stretch. If a is greater than 0 but less than 1, we know the outputs are not increasing as fast as they were originally, okay? So it's a slower rate than before. That rate of a, slower, so it's a vertical shrink. So without graphing, if our parent function is still 2 to the power of x, and we have this new function, y equals 4 times 2 to the power of x minus 7, how would they compare? Well, notice we have 2 changes to this equation, right? We've got this multiplier of 4, and we also are taking away 7. So we have 2 transformations happening here. We know that 4 times that multiplier is going to be a vertical stretch of 4. So those outputs are going to be 4 times as fast as they were before. And by taking away 7 from the outputs, we're shifting it down 7 units. So for pushing it down, that means our asymptote is also going to go down 7 units. And so we know that is going to be at y equals 7. No impact to the domain. These were only changes to the outputs, right? The y values, not the x's. But again, by lowering it down 7, we now know the range that the y's have to be greater than -7. And we can get all this just from the equation. We don't even have to look at the graph. So we want to talk about these transformations, right? And in our previous lessons, we talked about a couple other transformations happening. And this is kind of our transformation equation, we'll call it. So we know a couple of things about it. We know that the a value, that multiplier, can either be a stretch or a shrink, depending on what the value of a is. So if a is greater than 0, and in particular greater than 1, we know it's going to be a times faster. If it's less than 1 but greater than 0, it's going to be a times slower, so it's a shrink. If a actually is a negative value, it's going to reflect it over the x-axis. B, again, determines whether it's growth or decay. So if B is greater than 1, we know it's going to be growth. If B is less than 1 but greater than 0, we know it's decay. Then notice if you have something being added or subtracted in with the x, the input in the exponent, that's going to be a horizontal change, going left or right. And notice it's the inverse of what you think it is. If something was being added to the x value, we're actually going to the left. And if it was being subtracted, it's going to the right. This is similar to what we were doing with our point slope form. And then our d value, the number at the back of the equation being added or subtracted, that's your vertical shift, up if it's positive or down if it's negative. And so if we think about the changes, the output changes come from the A and D positions, and the input changes happens in the C position. So if we're talking about from a tabular point of view, we know our original parent function. We could fill in the parent function of whatever the base was for our x and f of x or our y values. And then based on the transformations we see, we can make adjustments to the inputs or output values. Again, the output values come from the A and D position. Inputs are the C. Apply those changes, and then we'll have the coordinates for our transformed graph. Okay. We also know where to look. We're talking about the domain, the changes of the inputs, and the range, the changes of the outputs. Let's show you an example of how we can use this transformation table to help us graph these functions and not necessarily have to rely on Desmos or graphing calculators to do this. So let's take a look at the equation y equals 2 times 2 to the power of x minus 4. So the first thing we want to think about is what would the parent function be? So we're going to look at the b value, right, the base, and that's 2 to the power of x. So we're going to focus on that as our parent function, and we're going to fill in our table of values based on that. So we're going to take our values for x and substitute them in to see what y values go with this. So we know 2 to the negative third power, that's 1/8. 2 to the negative second, that's 1/4. 2 to the negative first is 1/2, because remember the negative exponent says it's belonging in the wrong position. So instead of the numerator, those are in the denominator. So again, 1/2 to the third power, 1/2 to the second, 1/2 to the first. 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. And 2 to the third power is 8. So if we plot those points on our graph, this is our parent function, 2 to the power of x. Now we're going to see what transformations occurred. So we look at our equation and we see that our a value is a 2 and our d value is a -4. So there are two transformations happening. A being 2 means that there's a vertical stretch of 2 times faster than it was before. And the -4 means there's a vertical shift down 4 units. And again, we typically talk about the transformations from the left to the right. So we're going to start with that vertical stretch of 2 first and apply that to our table of values. So it's 2 times faster than it was before. So we're going to take all these outputs and multiply them by 2. And then to show we're going down 4 units, we're going to take these outputs and subtract 4 from them. So again, let's do the multiplier of 2. So we take all these y values that we have here in our table from the parent function, and we multiply them by 2, and we would get 1/4, 1/2, 1, 2, 4, 8, and 16. Now we take those values and we apply the vertical shifting down of 4, so we're going to subtract 4 from each of those values. And so we've got our -3.75, -3.5, -3, -2, 0, 4, and 12. There are no other transformations to take care of. So our inputs, x, and our outputs are the y's that ended with our last transformation. So we're going to plot the points from the x column and what we have here in green to show the transformation that occurred with both of those items being applied, the stretch of 2 and going down 4 units. So if I do that, I plot my new points. I'm doing this in purple. And then I'm going to connect them to show that I've got my exponential growth equation because I had 2 as my base b value, and I can see what's happened from my original point of view. We also can't forget that we had that horizontal asymptote at 0, and by shifting everything down 4 units, it's now at y equals -4. So we have the horizontal asymptote, y equals -4. That impacts your outputs, so we could talk about the range. Our range, the outputs cannot be a value of -4 or below, so they have to be above that. So if we're filling in what we know, the range is going to show that y is greater than -4. So therefore we have our left parenthesis, -4, comma, positive infinity, right parenthesis. There are no restrictions on our domain, so that can be from negative infinity to positive infinity. We can see that we do have an x-intercept on the graph right here at 1, 0. And we can see our y-intercept is at 0, -2. And again, our asymptote, it's an equation, y equals -4. So when we're asking you to show graphing exponential functions using the transformations, this is the expectation. We start the table with our parent functions. You find the b value and you write that down at the top of your table, and you substitute your standard -3 to 3 counting by ones to see the original outputs. Then you apply the transformations, and again we go from left to right. So if we had any stretches, we would do that first to the outputs. If we had any horizontal shifts left or right, we would apply that to the inputs. Remember, those would be shown up here with the x. Then we look at the back of the equation. That's going to be a change to the output. Okay, minus going down, so we're taking it away. Plus would be going up, we'd be adding it. Whatever your table ends with for the input and the output transformations, those are the points that you're plotting on your graph, and we want to see distinct points. I would say at a minimum 3, maybe 4 points, so you can shade the curve of your exponential function clearly for growth or decay. We also want to make sure that we're showing the asymptote with a dashed line, showing that's the boundary of the outputs. It cannot equal that value, but it will approach it and never touch. So now you're going to do some more practice graphing your transformed exponential functions, and again talking about key features like domain, range, x-intercepts, y-intercepts, and asymptotes.